Next, we discuss a parallel connection. There are also two kinds of parallel connections, that is, a dot on the same sides and a dot on the different sides. We first analyze the former. For such a circuit, we need to write KVL for this path and this path, and use KCL for the node at this time. And then we have simplified the three equations. We can write the expressions of the port voltage and the current like this. So we can know that LEQ of the parallel connection of the dots on the same side is like this. But it should be noted that the result and the derivation process are troublesome. Let's look at how to simplify the analysis process. We might as well substitute the KCL equation into the two KVL equations. That is to say, substitute I2 equals I minus I1 and I1 equals I minus I2 into the term and simplify them. We can get what's the benefit? We might as well have a look. I is the current of the common branch, and I1 and I2 are two branch currents. That is to say, we can construct an equivalent circuit without mutual inductance, whose equations of the port voltage and current are also in this way. What kind of characteristic does the common branch have? Yes, it needs an inductor and its inductance is M. For branch 1, it also needs to be an inductor whose inductance is L1 minus M. Branch 2 also needs an inductor whose inductance is L2 minus M. You can verify that the equations of such a circuit are also these three. The equations of the port voltage and current of the circuit without mutual inductance and the original circuit with mutual inductance have the same form and parameters, so they are equivalent. So what is this help? For such an equivalent circuit without mutual inductance, we can write the expression of LEQ directly by the serial parallel connection of this inductance, which is the exercise for you. Similarly, for the parallel connection with the dots on the different sides, we can also write the equations of the port voltage and current as this form. Having the experience, we can draw the corresponding equivalent circuit conveniently, that is, you can verify that the circuit without the mutual inductance and the parallel connection circuit, the dots on the different sides have the same equations. So we can easily write the equivalent inductance of the circuit without mutual inductance by serial parallel connection, that is, to say, having the decoupling equivalent circuit, we don't have to write so many equations and remember expressions of the equivalent inductance. We only need to remember that for parallel connection of the dots on the same sides, there is the inductance of M on the main path, and the inductance of the two branches should subtract M, respectively. For the parallel connection of the dots on the different sides, we only need to remember that there is the inductance of negative M on the main branch. The inductance of the two branches should be add M, respectively. Having two very concise conclusions, all results are natural.